It is permissible to use rebar as a grounding electrode and conductor in a grounding system according to the National Electrical Code. The rebar must meet specific requirements. Firstly, the rebar must be at least 20 feet in length. Secondly, the rebar must be electrically continuous throughout its length. Thirdly, the rebar must be embedded in at least 2 inches of concrete that is in direct contact with the earth. When installing the rebar grounding system, connect a grounding conductor at one end of the building to the rebar electrode, using an approved grounding electrode clamp. Connect a grounding conductor from the continuous rebar grid at another location to the water pipe where it enters the building. All connectors and connections must be encased in concrete that is at least 2 inches thick. The National Electrical Code requires that a supplemental grounding electrode be installed unless the grounding electrode system consists of an underground water pipe that is at least 10 feet long and in direct contact with the earth. In this case, a supplemental grounding electrode may not be necessary. It is recommended to consult with a qualified electrician to determine if a supplemental grounding electrode is required. Using rebar as a grounding electrode provides a low-resistance grounding path, reduces the potential for electrical shock, and protects electrical equipment from lightning strikes and other electrical hazards. The NEC specifies requirements for grounding and bonding to ensure electrical safety. Grounding electrodes, such as rebar encased in concrete, play a crucial role in providing a path for fault current to return to the source, thereby tripping over current protection devices and minimizing the risk of electrical shock. The requirements for the length of the rebar, the thickness of the concrete encasement, and the electrical continuity of the rebar are all designed to ensure that the grounding electrode has sufficient capacity and conductivity to effectively carry fault current. The bonding of the grounding conductor to the rebar and the water pipe creates a low impedance path for fault current, which helps to minimize voltage rise during a fault and further reduces the risk of electrical shock. The need for a supplemental grounding electrode depends on the effectiveness of the primary grounding electrode, which in this case is the rebar encased in concrete. If the rebar electrode meets the NEC requirements and provides a sufficiently low resistance to ground, a supplemental electrode may not be required. However, if the resistance to ground is too high, a supplemental electrode, such as a ground rod or plate, may be necessary to improve the overall grounding system performance. It is important to consult with a qualified electrician to determine the specific grounding requirements for your installation and to ensure that the grounding system is properly installed and tested. Electrical codes, like the NEC, are designed to safeguard persons and property from hazards arising from the use of electricity. Compliance with these codes is essential for ensuring electrical safety. Grounding and bonding are critical components of an electrical system, providing a path for fault current to return to the source and minimizing the risk of electrical shock. The NEC provides detailed requirements for grounding and bonding, including the types of grounding electrodes that are permitted, the size of the grounding conductors, and the methods for bonding different parts of the electrical system together. The purpose of grounding is to provide a low impedance path for fault current to return to the source. This path allows the overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and energize the circuit, preventing electrical shock and minimizing damage to equipment. Grounding electrodes are typically made of conductive materials, such as copper or steel, and are buried in the earth to provide a connection to ground. Bonding is the process of connecting different metal parts of the electrical system together to create a low impedance path for fault current. This includes bonding metal conduits, metal enclosures, and metal water pipes to the grounding system. Bonding helps to equalize the voltage between different metal parts of the system, reducing the risk of electrical shock. The size of the grounding conductor is determined by the size of the largest ungrounded conductor in the circuit. The grounding conductor must be large enough to safely carry the maximum fault current that could occur in the circuit. The NEC provides tables that specify the minimum size of the grounding conductor based on the size of the ungrounded conductor. The methods for bonding different parts of the electrical system together are also specified in the NEC. These methods include using bonding jumpers, bonding bushings, and other approved bonding devices. It is important to follow the NEC requirements for bonding to ensure that the electrical system is properly grounded and that the risk of electrical shock is minimized. The rebar grounding electrode system must meet all the requirements outlined in the National Electrical Code, specifically Section 250.52, which pertains to grounding electrodes. This section details what constitutes an acceptable grounding electrode. The rebar must be at least 20 feet long and 1/2 inch in diameter. The rebar must be encased in at least 2 inches of concrete. The concrete must be in direct contact with the earth. These requirements are designed to ensure that the rebar electrode provides a reliable and effective path to ground. The electrical continuity of the rebar is also critical. All sections of the rebar must be securely connected to each other to ensure that the entire length of the rebar acts as a single grounding electrode. This can be achieved by welding the sections of rebar together or by using approved mechanical connectors. The grounding conductor must be connected to the rebar using an approved grounding clamp. The clamp must be made of a material that is compatible with both the rebar and the grounding conductor to prevent corrosion. The grounding conductor must be sized according to the requirements of the NEC, based on the size of the service entrance conductors. The connection between the grounding conductor and the rebar must be accessible for inspection and testing. This means that the connection should not be buried in concrete or otherwise obstructed. A supplemental grounding electrode is typically required to augment the rebar electrode. A ground rod is a common type of supplemental grounding electrode. The ground rod must be at least 8 feet long and must be driven into the earth until at least 8 feet of its length is in contact with the soil. The ground rod must be located at least 6 feet away from any other grounding electrodes. The grounding conductor from the ground rod must be connected to the main grounding busbar in the electrical panel. The water pipe can be used as a supplemental grounding electrode if it meets certain requirements. The water pipe must be made of metal and must be in direct contact with the earth for at least 10 feet. The water pipe must be electrically continuous throughout its length. The grounding conductor from the water pipe must be connected to the main grounding busbar in the electrical panel. The connection to the water pipe must be made within 5 feet of where the water pipe enters the building. The NEC requires that the resistance to ground of the grounding electrode system be 25 ohms or less. If the resistance to ground is greater than 25 ohms, a supplemental grounding electrode must be installed. The resistance to ground can be measured using a ground resistance tester. The ground resistance tester applies a small current to the grounding electrode and measures the voltage drop. The resistance to ground is calculated using Ohm's law. The NEC also requires that the grounding electrode system be inspected and tested periodically. This is to ensure that the grounding electrode system is still effective and that it meets the requirements of the NEC. The inspection should include a visual inspection of the grounding electrodes, the grounding conductors, and the connections. The testing should include a measurement of the resistance to ground. If any problems are found during the inspection or testing, they should be corrected immediately. It is important to consult with a qualified electrician to ensure that the grounding electrode system is properly designed, installed, and tested. A qualified electrician will be familiar with the requirements of the NEC and will be able to ensure that the grounding electrode system meets all applicable codes and standards. The location in Florida may influence the grounding requirements due to soil conditions and lightning activity. Soil resistivity in Florida can vary depending on the region, with some areas having highly conductive soil and others having less conductive soil. High soil resistivity can make it more difficult to achieve a low resistance to ground, which is necessary for effective grounding. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes or to use ground-enhancing materials to improve the conductivity of the soil. Florida is also known for its frequent lightning activity. Lightning strikes can cause significant damage to electrical equipment and can pose a serious safety hazard. A properly designed grounding system can help to protect electrical equipment from lightning strikes and can reduce the risk of electrical shock. In areas with high lightning activity, it may be necessary to install a lightning protection system in addition to the grounding system. A lightning protection system typically consists of lightning rods, conductors, and grounding electrodes. The lightning rods are designed to intercept lightning strikes and to safely conduct the lightning current to ground. The conductors are used to connect the lightning rods to the grounding electrodes. The grounding electrodes provide a path for the lightning current to dissipate into the earth. The design and installation of a lightning protection system should be performed by a qualified lightning protection contractor. The grounding electrode conductor, or GEC, is the conductor used to connect the grounding electrode to the equipment grounding bus or grounded conductor of the system. The size of the GEC is determined by NEC Table 250.66 based on the size of the service entrance conductors. The GEC must be made of copper or aluminum and must be protected from physical damage. The GEC must be installed in a raceway or cable armor if it is exposed to physical damage. The GEC must be connected to the grounding electrode using an approved grounding clamp or connector. The grounding electrode system must be installed in a manner that minimizes the risk of corrosion. Corrosion can damage the grounding electrodes and conductors, which can reduce the effectiveness of the grounding system. The grounding electrodes should be made of materials that are resistant to corrosion. The grounding conductors should be protected from corrosion by being installed in a raceway or cable armor. The connections between the grounding electrodes and conductors should be made using corrosion-resistant connectors. The grounding electrode system should be inspected periodically for signs of corrosion. If any corrosion is found, it should be corrected immediately. The equipment grounding conductor, or EG, is the conductor used to connect the non-current carrying metal parts of equipment to the grounding system. The EGC provides a path for fault current to return to the source, which causes the overcurrent protection device to trip and de-energize the circuit. The EGC must be sized according to NEC Table 250.122, based on the size of the overcurrent protection device protecting the circuit. The EGC must be made of copper or aluminum and must be installed in the same raceway or cable as the circuit conductors. The EGC must be connected to the metal parts of the equipment using an approved bonding jumper. The bonding jumper must be sized according to NEC Table 250.102, based on the size of the circuit conductors. The NEC provides specific requirements for grounding and bonding in different types of occupancies such as residential, commercial, and industrial. These requirements are designed to ensure that the grounding system is appropriate for the specific hazards present in each type of occupancy. In residential occupancies, the NEC requires that all metal water pipes, gas pipes, and metal building frames be bonded to the grounding system. This is to prevent these metal parts from becoming energized in the event of a fault. In commercial occupancies, the NEC requires that all metal raceways, metal enclosures, and metal equipment be bonded to the grounding system. This is to provide a low impedance path for fault current and to minimize the risk of electrical shock. In industrial occupancies, the NEC requires that all metal machinery, metal piping, and metal structures be bonded to the grounding system. This is to protect workers from electrical hazards and to prevent damage to equipment. The NEC is constantly being updated to reflect changes in technology and to improve electrical safety. It is important to stay up to date on the latest NEC requirements to ensure that your electrical system is safe and compliant. You can obtain a copy of the NEC from the National Fire Protection Association (NFPA). You can also find information about the NEC on the NFPA website. It is always recommended to consult with a qualified electrician to ensure that your electrical system is properly designed, installed, and maintained. A qualified electrician will be familiar with the requirements of the NEC and will be able to ensure that your electrical system meets all applicable codes and standards. Firstly, ensure the rebar is clean and free from rust or coatings that could impede electrical conductivity before encasing it in concrete. Secondly, when connecting to the rebar, use exothermic welding, also known as CAD welding, for the most reliable and corrosion-resistant connection. Mechanical connectors are acceptable, but should be listed for direct burial in concrete and regularly inspected. Thirdly, consider using a ground-enhancing compound around the rebar electrode to lower the ground resistance, especially in areas with poor soil conductivity. Fourthly, document the installation thoroughly, including the location of the rebar, connection points, and ground resistance measurements. Keep this documentation readily available for future inspections and maintenance. Fifthly, when connecting to a metallic water pipe, ensure there is continuity throughout the piping system. Many modern water systems include non-conductive sections, which would negate the effectiveness of the water pipe as a grounding electrode. Sixthly, when using both the rebar electrode and a water pipe electrode, ensure they are bonded together to create a common grounding system. This minimizes potential differences and improves the overall effectiveness of the grounding system. Seventhly, periodically test the ground resistance of the grounding system. The NEC recommends a ground resistance of 25 ohms or less. If the resistance is higher, additional grounding electrodes may be needed. Eighthly, be aware of local amendments to the NEC. Some jurisdictions may have stricter requirements for grounding and bonding than the national code. Ninthly, consider using a concrete mix specifically designed for grounding electrodes. These mixes often contain additives that improve conductivity and reduce corrosion. Tenthly, install a grounding electrode inspection well to allow for easy access to the rebar electrode for inspection and testing. This can simplify future maintenance and troubleshooting. When dealing with electrical systems, safety is paramount. Always to energize circuits before working on them and use appropriate personal protective equipment or PPE, such as insulated gloves and safety glasses. If you are not comfortable working with electricity, consult with a qualified electrician.